So after having introduced change detection algorithms and having looked at simple deterministic approaches, now it's the time to move away from determinism and introduce probabilistic tests. And let us state once more why we need them. The issue is that if you have a signal over time that is normally 0, but sometimes you can have this kind of behavior, but you know that by itself this is not a fault. If you want to determine bounds for your limit check, then you need to have a bound like this above and this below, for instance. This assuming that you don't want to have a lot of false alarm rates, because you can also have a bound that is smaller. But then you know that your false alarm rate can be high. So every time that you have this kind of behavior, you have a false alarm. So you see, if I have bounds that are deterministic, so crossing them will lead to you saying there is an anomaly with a probability 1. You are sure about that. When the performances that you get in terms of false alarm rates and misdetection rates, they are not so good. It would be nice to really have a bound like this, but now that with some probability this bound is going to be crossed. And if you know what is the probability of this event, actually you can characterize this. So from a point of view of performances, having a deterministic bound is not good. We want to have probably a probabilistic bound. But the other reason is that sometimes it is simply impossible to have bounds. You may consider the case of a true random variable, like a Gaussian. Ideally, mathematically, these objects have no bounds. If you look at a random variable, a Gaussian, you know what is its mean, you know what is its variance, you know that for a Gaussian, 99 point something % of the samples are between 3 sigma plus and minus of the mean. But this doesn't tell you what is the ultimate bound of the other samples. And actually, it is unbounded. So a Gaussian variable can be infinite with probability 0. With probability 0, but it doesn't mean that it is impossible that you get an infinite value for a sample. It's a probability that is 0, but it is not an impossible event. So if you really want to have bounds that always hold, and you have a random variable, it is not working. So we need to move away from deterministic bounds and deterministic checks and have a different way. And probabilistic tests are actually doing that. As you can imagine, probabilistic tests are not looking at single values, but are looking at statistical quantities, statistical ways of describing your signal in terms of the mean, the variance, or other moments. And this allows them to cope effectively with random variables. So in moving away from determinism and embracing a stochastic probabilistic approach, then we need to introduce a new dimension in describing our signal. And this dimension is the one encoding probabilities. So we need to introduce and start looking at the probability density function of the signal. So we need yet another dimension. And this dimension is mapping values of z over the probability of z having that value. So for a Gaussian variable with zero mean, we have this usual and well-known shape. And the PDF, just to remind you about that, is something that tells us if you want to know what is the probability of z having a value between this minimum and this maximum, you take the PDF and you integrate. So the area that we have here is the probability of z having a value in this interval. So this is what the PDF is telling us. Anyway, higher value of the PDF means higher integral over the same interval. So you easily see that when the PDF is bigger, then the probability of getting samples of z is higher. So if we get a value of z that is here, so if we have this z1, let us assume again now that z is a scalar. Well, the value of the PDF is high, so we are going to deduce that this is a likely event. Indeed, likelihood is the value of the PDF evaluated for z1. But if we get a sample of that here, the value of the PDF is small, and then this is an unlikely value. So a probabilistic test, some way, is going to detect a boundary between values that are likely and values that are unlikely based on the PDF. And these ways of proceeding is actually doing hypothesis testing on random variables. You may ask, okay, this example was about scalar z. How am I going to operate if z is not scalar? Well, there are two ways. One way would be to reduce the dimension again by taking the norm of z, and so you get a scalar again. And this means that you need to have a way of defining what is the PDF of the norm of your vector, which is usually quite a different thing than the PDF of individual components. Or another way is to introduce a multivariate PDF for your multidimensional data. And we are touching upon both approaches in the next lecture when we address more advanced probabilistic methods. For now, let us stick to the simple case of z being a scalar. I started by introducing the PDF of z, which is a way of representing the nominal behavior of z as a random variable. But having a PDF is quite a lot of information. In a lot of situations, people have no idea what it is, the PDF of the nominal behavior of something. But everybody, probably most of people, know what is the mean, and quite some people know about what is the variance. And these are two simple, compact, and still very useful way of describing the nominal behavior of this random variable z. And just to remember, when you have samples of z and you want to compute the mean of samples, and you get samples not all together but just one at a time, you can use these two formulas to compute a recursive value of the mean. Okay, why it is important, why I'm telling you now? It is because normally there is no ideal a priori way of computing the mean and the variance of your variable z in normal condition. Sometimes you have, but sometimes just you don't. So you need a way to compute this mean and variance from samples. So this is what statisticians do. They collect data and they compute the empirical mean and the empirical variance. This is the way of calling the mean and variance when you compute it from samples. So the idea would be, in our case, to take a lot of samples of z in nominal conditions. So I take measurements of my heart rate when I know that I am not ill in nominal conditions. I take all these samples and I compute the mean and variance of them. This is going to represent the nominal value of the mean and the variance. You may remember from courses about probability that the empirical mean and variance, they are not going to be the same as the true mean and variance, unless you have an infinite number of samples. So you know by the law of large numbers that if the number of samples that you are collecting tends to infinite, then the empirical mean and variance, they tend to the true one. So we are both making the assumption of having a large number of samples, but also we are showing in the next slides how to take into account the case of small, non-infinite number of samples and still have a way to compute probabilistic tests in a robust way. Okay, so let us move further. So let us assume that we have the true values of the mean, mu, and the variance sigma for now. How are we going to use them in order to build a test? Well, this test is not going to surprise you. In the end, will be a limit checking test. But the difference now is that you check a statistical description of your variable against the nominal one. So in this simple case, we can check the mean and the variance that we get from a set of data, so the empirical mean mu hat and sigma hat, against the nominal value of the mean mu or the variance sigma. Now, the key thing to remember when doing that, the important fact is that while the true mean mu and sigma are deterministic quantities, that is, you know them, the empirical mu and the empirical sigma, when you compute them from a sample set with a finite number of samples, they are going to be random variables themselves. Okay, wow, so now you have two levels of random variables. The variable z you want to check is one random variable, but the empirical mean mu hat and the empirical variance sigma hat computed from samples of z, they are itself random variables. And now we are talking about these second ones. So we want to build a test for z based on mu hat and sigma hat that are random variables. And so we need to define thresholds on mu hat and on sigma hat. For the case of a Gaussian variable z, so if z is a Gaussian, if you compute the empirical mean mu hat turns out to be a Gaussian itself. So this is some fact probably you know from probability courses. So if you're going to plot the PDF of mu hat itself, let us stress this again. So these axes here represent possible values for mu hat. And this curve here is the PDF of mu hat. We denote it as P of mu hat. It is a Gaussian and it is centered over mu 0. Mu 0 is the nominal value of the true mean mu of z. So z is a Gaussian and its nominal mean is mu 0. And then if we have samples of z, z1, zn, and we compute mu hat itself is a Gaussian, and its mean shouldn't come as a surprise, is mu 0 again. This is telling the fact that the empirical mean is an unbiased estimate of the true mean. So there are a lot of means here, but the mean of the empirical mean is the mean nominally. So that's the thing you need to have clear on your mind. So let's look at this Gaussian here. Now we have it here. If we want to know whether a value of mu hat that we just computed is from a nominal condition or not, we can draw two bounds on this, a lower and an upper bound. One here and one here. That is, try to imagine this. We have a lot of samples of that coming through. We have a time window that is moving, like in the previous examples we had. We take all the values of z in that time window. With all those values, we compute a value of mu hat. So for one time window z, we get one value of mu hat. And we have it, and let us assume it is this. It is not going to be exactly mu0. Why? Because we have measurement noise, because our time window is short. If we had an infinite time window, it will always be here. So actually, this is telling us that as the time window is getting bigger, so as the number of samples is getting bigger, the variance of this is getting smaller. So when n tends to infinity, this is going to squeeze here. So it squeezes, variance small, and you get Dirac delta here. But OK, in a normal situation, this is not going to happen. So now the question is, I computed mu hat from a time window of data, and I got this value. Is this good or bad? So we check. If it is between this value that is called here mu alpha over 2 and mu 1 minus alpha over 2, we are good. Otherwise, we are bad. How did we come up with these boundaries? The idea is that, as I said before, the probability of mu hat occurring in an interval that starts here and go to minus infinite in this direction, it is equal to the integral of the PDF of mu hat from minus infinite to this. I can choose the boundary such that this integral, the area of that, is alpha over 2. Now, for symmetric reasons of the Gaussian PDF, I can select another threshold here such that now the integral of the PDF from this value up to plus infinite is alpha over 2 again. So if we sum these together, I get alpha. So the area of this and the area of this is alpha, which means the probability of mu hat to occur here or here is equal to alpha. So now probably you see where we are going. If I choose alpha to be conveniently small, like alpha is equal to 1%, then I know that in normal condition, just because of noise and so on, the empirical mean mu hat will occur here or here with that small probability, which means in the rest of the cases, 99% of the cases, mu hat is here. So this is the normal, represents normal event, represents our physiological behavior of the system. Here and here is representing what? Is representing areas that either are physiological but really unlikely, or areas that are pathological. So in a probabilistic test, I cannot tell. But what I can do is have this test and say, whenever you have a sample here. These represent your system is healthy with some 99% probability. And whenever you get a sample here or here, you say, look, I'm not sure, but with a very small probability, like 1%, your system is healthy. That was just bad luck with the noise in the system. Or your system is faulty. So now it is your turn to decide what to do. So probabilistic tests are actually doing that. You trade in performances with certainty. Usually, having better performances is much better than losing some certainty. So people are preferring probabilistic tests. We just need to accept this different point of view. So we don't get certain answers, we get answers with a probability attached to that. As the area here is equal to 1 minus alpha, 1 minus alpha is actually what we call the confidence or significance level. So again, if we get a sample here with 1 minus alpha confidence, we accept the hypothesis. So no change happened. The interesting thing is that if we run this test many and many times and we compute the false alarm rate of the test, this is equal, as you can imagine, to alpha. How are we going anyway to compute in practice this test? So as we said, again, so we start from Z, set of samples of Z, we compute mu hat. Once we have mu hat, we need to compute another quantity that is called the p-value. The p-value is the probability of getting a value of mu hat that is as extreme as or more extreme as the value of mu hat that you actually got. So let's explain this concept by making use of this plot. So let us assume that in one experiment you get a value of mu hat that is exactly equal to mu 0. The p-value of that is 50%, because normally 50% of your samples are smaller than the one that you got, and 50% of the samples are bigger than the one that you got. So this is a perfect symmetric situation. Instead, if in one experiment your mu hat is exactly equal to this threshold value, mu alpha over 2, then the p-value is equal to alpha over 2. Because the probability of getting a mu hat that is this one, or more extreme, in this case smaller, is alpha over 2 by definition. If in another experiment you get a mu hat that is equal to this value here, this border, mu 1 minus alpha over 2, then the p-value is again alpha over 2. So the probability of getting this value or more extreme, bigger, is alpha over 2. So what is making a bit tricky the definition of the p-value in this case is that if you look at this test as we define it, this is what is called a two-tailed test. So you are looking here at two different tails. So the tails on the left for very small and unlikely value of mu hat, and the tail on the right, very big and unlikely value of mu hat. The p-value is telling you the probability of getting in that given tail there or even farther away from the nominal value. Computing that in this case requires you, first of all, to check on which side I am with respect to mu 0. So if I am on the left side, the p-value is actually equal to the cumulative density function. Because if I get a mu hat here, the cumulative density function is actually the integral of everything that I have on the left. So when I am on the left side, the p-value is equal to the CDF. But if I am on the right, the p-value is equal to 1 minus the CDF, because the CDF is the probability of being there or on the left. But in this case, I want the probability of being there or on the right. So I need to take 1 minus the CDF. In most of the softwares that are implementing hypothesis testing, this is already taken care of. But if you want to write your own code, please take in consideration this small detail. By the way, this is also why the border that we have here, this threshold, is called mu 1 minus alpha over 2, because this is the value of mu where the CDF is equal to 1 minus alpha over 2. So the probability of having a value here or the left is 1 minus alpha over 2. So please take in consideration these details, because they are important once you want to implement your own code. Anyway, whatever. Once you compute this p-value, the only thing that you need to check is whether this is bigger or smaller than the significance level that you want. So if the p-value is equal to or smaller than alpha over 2, it means I am either this or this tail. So there had been a change. If the p-value is not, then everything is okay. Okay, so this is the basic approach on which hypothesis tests, probabilistic hypothesis tests are built. Now we're going to see a few famous and widely used tests that you can easily implement, as they are already implemented in many softwares like MATLAB, Mathematical, Excel itself. And let us introduce the t-test. So here we are assuming that we have a variable z, of which we know the nominal value of the mean, that we call mu. And we want to test whether the mean of z is indeed mu or changed. So this is useful if we have a fault that is going to change the value of z in the mean. For instance, in the case of the heart rate, I can have a nominal behavior of my heart rate that is something random distributed around a nominal value mu. And I want to see whether this changed, either up or down. So as you can imagine, this kind of test is a two-tailed test, because unlikely values are either bigger than mu or smaller than mu. One way to do that is actually to implement what is called the t-student test, and in particular the one sample t-test. This test is based on computing yet another random variable t. T is equal to the empirical mean mu hat computed using n samples minus the nominal mean mu over the empirical variance sigma hat computed over the same set of samples divided by the square root of n. So this means that to implement this test, you need to take your variable z, which we assume is a normal variable with mu as a mean and some sigma as a variance. You take samples of that. How many? N samples. And using them, you compute two empirical quantities, so mu hat and sigma hat. So taking these and mu, the nominal one, and using the formula that we have there, you compute T. So the nominal mu is a deterministic quantity, we know them, but mu hat, sigma hat, and T, then, they are random variables because we compute them over a set of samples, so they are influenced by measurement noise. You have a different set of samples, you get a different value of mu hat, of sigma hat, and thus of T. Anyway, out of a set of samples, I get only one sample of T. So this is why this is also called a one-sample t-test. Once I have T, I carry out the test, and I compute its p-value, which we denote in green. And then, using tables or a software, and using a significance level, alpha, we get our answer. So we know that the T variable has a specific distribution that is called the T-student with n-1 degrees of freedom. So there are different T-student distributions. It is a whole family, and every member of the family is parameterized by the number of samples that you used to compute it. So if you use n samples, then the T variable you get is distributed with n-1 degrees of freedom. So what you need to do is to compute the p-value. Sorry, the information of the tables is used to compute the p-value actually, and not here. So using information from tables of T, so basically the information on the CDF of T, you can compute the p-value, and then you compare that with the significance level alpha that you define. And of course, pay attention whether you are doing a two-tailed or one-tailed test, but usually software implementations that are available in Excel or MATLAB will take care about that. So if you basically do this test, you can answer whether you had a change or not. So if you get a high value of the p-value, then you are in a normal condition. But if you get a smaller one, then you get, probably you are in one of these conditions here. So remember anyway that the significance level is defined as 1 minus alpha. So when you're using some software to do that, pay attention that you understand whether the software wants alpha or 1 minus alpha as a parameter. Anyway, there are different tests that you can implement in this way. And another test is possible in the case that you don't know mu. So as we said, in practice it's difficult to know ideally from first principle what should be the average of a variable. What we can do is to compute that from samples during healthy conditions. But then we have a sort of chicken and egg problem. So how can we determine what are healthy conditions before we design a test to detect what are healthy conditions? So this chicken and egg problem is solved by assuming that when you start collecting samples, you are in healthy conditions. So initially, your system or your patient are healthy. And a fault is happening at some time after you started collecting data. So now the issue is both then estimating what is the nominal value here and detecting this change and what is the new nominal value. Okay, now we make a bigger drawing. So our data initially is following a mu equal to mu0. But we don't know the value of that. Then we have a fault. And our data will be distributed with a new mean equal to mu1. So they are both deterministic quantities, but we don't know them. Instead, we have two time windows that we move around the data. We draw with a blue color and with a red color. Okay, these are windows of samples that we move over time. So as we get samples, let's assume we got samples until here. We build two time windows from here to here and from here to here. We use the samples inside them to compute two quantities. One is called mu0 hat, so the empirical mean that we have inside of the first window, and then mu hat 1, the empirical mean inside of the second time window. So initially, we don't know whether we had a change or not. So in this drawing, you see that I draw them exactly such that they occur around the change time instant. But when you are implementing this approach in practice, you have no idea whether a fault, a change happened or not. So these windows are moved forward as you have more new samples, you move them. But let us think how they look like initially. So initially, when I have no fault, these windows are both in a region here. And what I expect is that the empirical mean mu0 and the empirical mean mu1 are pretty much the same. We know that they are random variables themselves, so their own mean is going to be the same. When I am farther in the future and the change already happened, both windows mu0, both the first and the second window will be here, and then I expect mu0 hat and mu1 hat also to be the same. And actually, they are random variables with a mean equal to mu1. When I am exactly like in this situation, such that the two are centered around the moment I have the change, then the one on the left has a mean equal to mu0 hat that is pretty much an empirical mean mu0 hat that is pretty much equal to mu0, except for the noise. And this one will have an empirical mean mu1 hat that should be pretty much equal to mu1. And the test I want to build is going to detect exactly this condition. And to do that, I compute yet another t-student variable, but this time it is different. Because as I have no information about this, I need to use values I estimate. So on the numerator now I have mu0 hat minus mu1 hat, which are both random variables, normalized by these terms that I have here, where I have the empirical variance in this time window, the empirical variance in this time window, and then the rest of the normalization factor depends on the number of samples n0 that I have here. So this has n0 samples, and the number of samples n1 that I have here. So in general, they don't need to be the same. Okay, so what happens? As we said, when both windows are on the left, then the test will not reject the hypothesis because both the empirical mean are the same, pretty much. When both time windows are on the right, well after the change happened, again, the hypothesis will not be rejected. So the only moment when they are going to be rejected is in this condition, because in this condition, mu0 hat and mu1 hat are going to be different. Well, this is a different behavior than this previous test. This previous test will tell you, okay, change. So once the change happened, this test will always tell you a change happened, because it is based on mu, that is fixed. This test instead is computing dynamically these values of mu. So we expect it to say to tell us as a result, no change, a change happened, and then no change. And that's the tricky part of it, because if you have a behavior like this one, when the fault is incipient, then initially mu1 hat will be different than mu0 hat, but not so much. Only when you have inside your time window enough samples that reached steady state in this new condition, then mu1 hat is going to be different enough. But then the problem is, as you move further these time windows to the right, then in the first time window, you also start to get some values with the new mean. So it is tricky. If the change you are looking for is very slow, this test one probably is not detecting it. So this is going to work for sharp, abrupt changes. Only one thing, please notice that now the t-student variable you get by computing this formula is distributed with n0 plus n1 minus 1 degrees of freedom. Well, that is all as before, the total number of samples that now are on two different time windows, minus 1. Now, we have seen some tests to check whether the mean of a signal changed. But sometimes we are interested in changes in variance. For instance, you can have a signal that always has a zero mean. So maybe this is an AC signal in some circuit. But normally it is like that, with some noise. But then because of a failure of an electronic component on the circuit, the noise level is getting much bigger. And this is what you want to detect. You want to detect a change in the variance of the signal. Because of course, if you compute the variance over a time window, here the variance is small, here the variance is big. Well, the idea is still the same. You take samples, you compute empirical statistics, and you compute some ratio, and you get a new random variable. And this is what is done in the chi-squared test. or actually, sorry, that's pronounced chi in English. So the variable that you get here, that is equal to n minus 1, the empirical variance sigma, and the change condition, over the nominal variance sigma 0 in nominal condition. This is distributed as a chi-squared random variable. So in particular, this is a chi-squared random variables with n minus 1 degrees of freedom, where again, n is the number of samples we used. Now, once you compute one sample of this chi-squared variable, the way to implement the test is a little bit different than what I've shown before, because the chi-squared variable is non-negative. And so when you implement the test, this is going to be a one-tail test. Said in other words, if we look at the CDF of chi, it is going to be something like this. I don't remember the exact shape of that, so my drawing is not accurate. But anyway, the CDF is 0 at 0, and then saturates to 1. So one way to implement the test is could be as before, to compute the p-value and check if the p-value is smaller than alpha, where 1 minus alpha is your significance level. Or you can also do another thing. You identify here in the CDF plot the point that has a CDF equal to 1 minus alpha, which means everything on the right has a probability alpha to occur. That is, the integral here, the area here, is equal to alpha. We call this value here chi-squared n minus 1, because we have n minus 1 degrees of freedom, 1 minus alpha. So that's the point where the CDF has a value of 1 minus alpha. Then the test is simply carried out this way. If the value you got, chi-squared, is bigger than this, so if you get a value here, then the null hypothesis is rejected. With confidence, 1 minus alpha. So this is another way of doing the same test without going explicitly through the p-value, but that's exactly the same thing. It is only that as we have a one-tailed distribution, it is easier to go through the CDF as we do it here. Okay, but what happens if we don't know the nominal value of the variance and we need to compute it from data? We can do that, and we get yet another test that is called the F-test. So the F-test is based on the ratio between the empirical variance before and the empirical variance after. And again, before and after means that, as in the previous case, we have two moving time windows that we slide over data, and we compute, in this case, sigma 0 hat in the first, sigma 1 hat in the second. We take the ratio, and the ratio is a random variable, of course, that is distributed as an F random variable with n0 degrees of freedom and n1 degrees of freedom. And now again, this is a ratio of positive quantities, then it is a positive quantity. So the test we are carrying is a one-tail test, and we can simply implement like this. So we check if the value we get for the F variable is bigger than this threshold. And this threshold depends on the CDF of the F variable with these degrees of freedom and these confidence level. 1 minus alpha. So again, this is something that either is available on software or you have tables in books. And the same issue as in the student test with 2 windows that I shown before, the same issues are present. So if the change in the variance is slow, then this test probably is not catching it. Okay, so there is one downside. And the downside is that to be able to verify and falsify the null hypothesis with good significance, you need a high number of samples. Why? Because as we mentioned before, when you are computing empirical quantities, if you have just a few number of samples, then this PDF that you see here, the PDF of the empirical quantity itself, is going to be very shallow and wide. And then detecting a change is difficult. If you have a lot of samples, if you have a number n of samples that tend to infinite, this thing, as we said, is squeezing and tends to be a direct delta. And then detecting a change is very easy, because pretty much everything that is not mu0 in this case will be detected as a change. But now, let's go back to the example of the 2 time windows. Having a lot of samples mean that these are very, very long. And having very, very long time windows is an issue because you need to wait a long time before you can fill them. And also, they are not really sensitive to changes that are short in time. So let us assume that after some time, this fold here is going down back to the nominal value. So the fold is intermittent. So if we have a time window this size, maybe we catch it because the size of the time window is less than the duration of the fold. But if I had a time window that is very, very, very long, because I want to have high significance in my tests, then the time window will include moments I have the fault and moment I have it not. And so the mu hat I computing is not going to be close to mu1. It's going to be something in between mu1 and mu0. And then the possibility of this test to actually tell you, hey, there is a change is small. So probably we are not getting it. And so we have this issue. We have on one side, we would like to have high significance. And on the other side, we would like to be able to detect faults that are very short in duration, or we want to detect them very quickly. So there is a balance. On one side, we have significance, which means a high number of n. And then on the other side, we have sensitivity of the test. And we get it for n that is small. So we want an 1 minus alpha that is big. And here we want a detection delay. We never introduced that, but let us call D the detection delay that is small. And so, according to having a small n, we move here, or having a large n, we move here, but we cannot have both, unfortunately. So similarly to the issue with the misdetection rate and the false alarm rate, actually it is the same issue. Because here we get small false alarm rate, but high misdetection. So we don't detect faults that are short. Here we have a small misdetection rate and also a low delay in actual detections. But false alarm rate is bigger. Well, this kind of compromise that must be reached is a constant in detection algorithms. So there is no way to build a fault detection algorithm where you can make happy both people that want this and people that want this. So you need to make a choice and decide where you want to stay. Anyway, still there are ways to improve this. So there are algorithms that allow you to get a good sensitivity and a low detection delay without compromising too much on significance. And these are algorithms based on likelihood that we're going to see in the next lecture. So today we have introduced the problem of change detection. We have introduced some deterministic approaches and some probabilistic ones. And one thing I didn't tell you, but please remember, most of the probabilistic tests, they are assuming that samples are independent. So differences in samples are just due to noise that is independent, white noise. If you have correlation between samples, then that's no longer so good. In the next lecture, we're going to see some advanced probabilistic tests. Thank you.